Some things about the finite fields, the numbers. So, many people got a question about what is field, what is ring, what's a vector space. I deliberately didn't go through the normal classical way, but to have a general feel for these objects, and so that way you can reflect on easily. So, in fact, whatever that additional mathematics part we require, I will cover as and when I go. So, sometimes we may have to, the order may have change a little bit. Okay, we couldn't exactly do it. So, I gave this, and I also mentioned in the class that you go and look over it. So, yesterday I gave extended GCD algorithm and convinced you that the algorithm converges, and what gives you out of that, the last but one reminder is indeed the GCD, and then using the GCD and the equations of the remainder theorem at that point, then you can work backwards and you could relate GCD as a linear sum of the arguments that to given with. So, then we showed that the GCD given AB, GCD is always can be expressed as a linear sum of its arguments. So, then you can take one of the arguments as modulo n, then that will give you a natural algorithmic way of computing inverses in a field. So, inverses in a structure, that is something like modulo n, and I wanted you to reflect on when it will be field and so forth, etc. Right. So, that is why by doing some of by examples, so you can feel about the properties that you require. So, most of the abstract algebra comes with abstract properties, so you need to think about what is given there and then start making properties on it, and so that is what the mathematics way of doing it, and there is no shortcut. So, you will have to actually learn one by one. Mathematics is not very difficult, but except that you will have to be aware of where you start with, and each step you need to go one by one. Okay, as and when you go, you will lead to a different. This is less like taking a journey and then becoming aware of the journey also, not just going only from beginning to the end. So, whereas in some other field you can probably do, say, in the morning one topic, afternoon another topic completely disregarded, but both can be of some use in those fields, especially in humanities and other stuff, but there is a different way of understanding the knowledge, whereas with mathematics it has to be slow and steady. Whereas, since we also have a very big task asset, within 10 days we need to get into the regenerative codes and the new codes for the storage, we have to make some compromises, and I initially stick to that having a finite field yesterday, and some of these slides which we will give you later, but idea is this actually making sure that the program that I said, there is a theorem proving version of that, why that indeed gives you a GCD, and how you can the GCD you can represent it as a linear sum of things, right. So, once you do that, I just quickly go over it, and so this is what actually I showed you this yesterday with some examples on it. So, how you can actually find the equations, etc., and that can be used for modulo n, and from there I have some slides that actually lets you about the properties of numbers modulo n when n is a prime or a prime power and so forth, and some of these results you can prove it just from the results that we have already developed, so it does not require anything. So, this actually tells you when for example, when you have n is a prime number, you get a particular type of residues, and when it is for example, you can prove like this is the number of elements and this. So, maybe what I will do is I will continue with the coding topic first, and then once wherever we need extra I will come back and to you, but you need to go through this maybe once after the break or something here. I will tell you, and there is a proof there, and I can probably give you some help on how to read about it and convince ourselves exactly this does the job. Okay, let us leave it at that side, and then we will move on to today's topic. Yesterday when we we looked at just a code, and what is the definition of a code. It takes information bits and converts and adds some parities, and we just described code as a collection of code words, and code words are some kind of a subset of a n-dimensional spaces, So we didn't really worry much about the structure of the field itself, but we just looked at the code words. And since it was a binary, it was not that difficult, and you could even the binary structure is linear, but we didn't use any of that. We just looked at the properties of a code and say what is the correcting capability, error detecting capability, and we also made use of some relations such as the relating the distance to the weight of a code word. And in fact, in case of a binary alphabet, finding distance between two code words, it is sufficient you take subtraction of these two vectors and look at the weight. So so using some properties of the weight, we showed that this distance is the Hamming distance is indeed is a distance, which means that it follows a triangular inequality. So we could also prove that the triangular inequality is possible, but we want to go to the next step. For example, we want to look at now chords over alphabet size, which is more than 2, but we will before going there, we will have to look at actually some of the constraints that these objects will tell us. For example, constraints on the length, constraints on the dimension, constraints on the distances that you get. So that tells us actually when we construct some code whether it is good or bad in those kind of things. So to have some initial, and there are a lot of interesting open problems still in some of these areas, even after so many years of study by many researchers. So let us look at the linear codes. Now here as a subspace, so already now I'm actually, you asked for initially what is a field and ring, and now we go into a space. And so at this discussion I will not go into formal definition of the subspace or something. There are excellent books available. Probably when we discuss today on this topic, and depending on people's doubts and everything, I can actually help you to read it from some text and be here, okay. And with some examples also, it may become what is this subspace, okay. And then we look at the representation of linear codes as a generator matrix and parity check matrix. This would be interesting. That will also kind of involve into linear algebra of these, and that is what is more important. So as in the previous section, we did consider some special structure associated with code words. So there it was just a sequence of symbols from FQ. So if you take a finite field, the code words are simply sequences from FQ. And the minimum distance of the code also we looked at it, but if you want to try to find the minimum distance of a code where there is no structure is given to you in advance, then you have no other choice but to go through every code word and find out its distance and list them and choose the minimum of them. And we looked at it, the complexity of that is how much? M, where M is the size of the code word itself. But as you can see that if you have a k down, k information bits and there n minus k parity bits, already the size of the code is exponential in the information size, that is k. So if and then there is a further quadratic function, it's a it's pretty expensive to do that. So can we now do something better with this case, and let us take a look at the definition of a linear code. So what is a linear code? Linear code is a block code over alphabet size, as I mentioned. So when you have a modulo q primary field, so always keep it in mind when I say FQ, a field now we will use, and the field is of the type prime numbers that we discussed yesterday. So obviously since we are now very much sure, everybody, we are working with residues, not some other objects. So we can always add over that field. So if you take a linear code is a block code, it's a finite field of order q, wherein pointwise addition of any two code words is also a code word. So we make just another condition. So we have a general code, we will now throw one condition. So okay, we want further, we will make it a restriction that okay, take any two code word and you add or subtract is the same code. Now some people may be thinking about this an idea of a subtract, what is the kind of thing. In case of a finite field, subtraction is not a big deal. I mean, you don't need to So for example, you have a vector, say you have a0, a1, say an minus 1 is a vector, and that is what where each ai now belongs to f q, okay. And now q, this f q is made out of set 0, 1, 2, you can say maybe q minus 1 of them, but depending on we haven't even specified what is q, but you can think of it's like a prime numbers at a time, but it will have a q minus 1. As you can see that q minus 1 has an effect of adding minus 1 to this, right, okay. So if I want to subtract another b0, b1 up to bn minus 1 is another vector, okay. So pointwise addition is simply taking pointwise addition modulo in that field. So whether it's modulo or something that we do will become much more clear, clearer later, but modulo q depends on what type of a field we use. But if it is modulo q, or let us say if it is in the finite field, I can always add. Now what is adding by subtraction? What is subtraction? So what is, for example, this is a and b, what do you mean by subtraction? Pardon? Yeah, you can have additive inverse. So one way to do it is you can take b and multiply by q minus 1, or a symbol in, okay, I will say that I'll write it here. So I take now b and you multiply a scalar, that's minus 1, that minus 1 in the field, okay. So for any, so now you tell me, I want to know we covered now g of p prime number, right. What is minus 1 in g of p? P minus 1 in this case, right, okay. So for every field there exists additive inverse of 1, and that let us call it minus 1. That minus 1 and the real number minus 1 are different. So when you are really subtracting means you are multiplying minus 1 to each and every element of this, sorry, b0, b1 to bn minus 1, and you multiply minus 1 times this, so I'll now minus 1 everywhere here, okay. So when I take a pointwise addition of a minus b, then it's well defined. So minus b0 is element in a field, minus b1 is an element in a field, then you will pointwise you will a0 minus b1, and you could do it, okay. So there will be some, this is the difficulty, but many people will follow, but as long as you understand now, then it will be easy. So already you are doing some kind of a vector space operation, because you are taking a scalar and multiply it, okay. So vector space is basically extending the structure that we have finite field to vectors. So now if we want to handle vectors, whatever we learned as finite field yesterday, we just make them as vectors and start working with it. Since you have more than one elements in a field, we need to also consider kind of what is called scalars. So with scalars, what it does is whatever that it does to the first element, the scalar effect will happen to all other elements. So you can define vector space in this form, and so now you can and then already once you have this vector space, I will be able to construct all these vectors using the what are called basis vectors. So if I have a length n vector space, so vector space of length n, polynomials, they are all interchangeable here. So as long as you understand the same meaning, then the concepts become much more easier to do. So you have to say, for example, you take a vector called 1 and you have all 0, another vector 0, 1, all 0, like that you can go, that exceeds n. So there are n such vectors, okay, and each one has a meaning in g of q. So now you can say any element in that vector space can be represented as a linear combination of that. So, for example, how do I represent A0 in 1? First take A0 multiplied by this, then I take A1 multiplied by this to AN minus 1 multiplied by this, then I take a sum of all of them, I get this. That is what the vector space is about. So, once you understand this calculation arithmetic, then you have to what mathematical proof will do, whatever we did for one of them, we try to extend it to that, what other properties gets extended. So, all that are logically mentioned, and that is why then we will make it okay, this is a distributive law, this is a this law, etc. So, once then it will be easier to follow. So, instead if you do not see this well and just try to look at the exams one, sometimes it becomes pretty difficult. So, I am now that part of things I intuitively assume, and whenever whatever that is thing required will come back and probably mention this and give it to you. So, you can also learn this thing. So, a linear code is now in that sense a block code of finite field or a Q where pointwise addition of any two code words is also a code word. So, with the code definition now we only threw extra a condition called linearity. So, now with linearity suddenly things becoming much easier, and let us say the first one, once you have a linear code definition, the first theorem fact, all 0 code word has to be present in a linear code. Do you see the point? Because let us say a particular one is a code word, that times Q minus 1 is also a code word. So, now you add them, that also should be a code word. So, that is actually getting a 0. So, whenever you have a linear code, you have all 0 code words. For a nonlinear code, that is not needed, that is the kind of thing. So, that one you can easily prove. So, for example, in any of the simple coding theory class and thing, these are the theorems you will get to prove. Okay. Then the minimum distance, so the next theorem goes is a little bit, so minimum distance of a linear code over FQ is the minimum Hamming weights of all non-zero code words in the code. So, you go there, so instead of now finding minimum distance now, in a linear code, I had to just to go and look at all the code words and pick the code word one with a minimum weight, and that will be the also minimum distance. Because now finding minimum distance between any two code words is basically finding the number of positions that differ, which is basically equivalent to using our previous day's theorem that you just take exclusive, you take the pointwise subtraction of these two code words and then find out the weight of that. And the linear code has already that word. Like for example, take one code word. So, the proof is already there. So, if code is linear, the distance between any two code words is equal to the Hamming weight. Now, if A is there, B is there, the difference will be also there in the code. So, I do not have to really compute the distance for every code word, I have to just to go and pick the code word with a minimum weight, and that will become the minimum distance of the code. So, this is one simplification that results because of the linearity. So, you can say that set of now n tuples over FQ with addition as a component wise addition and a scalar multiplication by elements of FQ is a scalar, that is a vector space, and that we refer as FQN. So, you just put a superscript n, that becomes the vector space. So, the properties of linear code, because now codes are linear, so the whatever that structure we talk about, that is already present in a bigger field size of FQN, because FQN has all the elements from FQ of size n, but the code is basically generated with only M, capital M, or which using k information bits. Hence, it has a q power k elements, which is much less than the number of vectors possible in the vector space, and it is linear. So, properties of the linear code you can took, then it satisfies whatever properties you require, but that is actually, so hence a linear code is a vector subspace of FQ1. So, the linear code, for example, has now F that is of the FQ n of the size of Qn, that has to be present in FQn. So, it should be within that. So, there are q power n elements, it is a big space of q power n elements, and so the code actually sits inside, but they are all related by linearity, and so it is a kind of substructure that sits inside it. Okay. So, one of the ways to see the subspaces, I give you some idea, simple examples. So, if you have a subspace, so let us take for example all vectors over binary field. Okay. So, you have a okay, we will only take simply example of length 3. You can see that so you have 0 1 0 1 0 1 0 1, then 0 1 1 0 0 1 1. So, by using 3 length word and the taking finite field as a binary 2, so there are exactly 8 different words are there. But out of that, let us take the first 2 bits. You can say that 0 0 in the first 2 bits, you can say 0 0 0 1 1 0 1 1 is also within the same structure, same word. But you can also now think of some word, for example 1 0 0 1 0 1 1 1 0 1 1 1 is also a subspace. Is it a subspace? Okay, let me. No. So, who identified? Okay. Why it is no? Exactly. So, that is not there. So, this can't be a subspace. I am just kind of thing. Then, but if I change it to 0 0 0 0, that is a subspace. Okay. So, that is the kind of definition that tells you about. So, linear code now is a C-dimensional subspace, but if you try to get subspaces of this type without really regarding, what you will do is you should have zeros. So, for example, another type of subspace you see is 0 0 0 1 1 1. Oh yes, that is also an interesting subspace, but that is also an interesting code, which is a repetition code, because in this there are 2 elements in the subspace, and one is all 0 all 1. It is a repetition code. Okay. So, this is the general things of a thing. So, now a definition, so linear code is a subspace of FQN. Now, so once you have a subspace, and so one of the traditionally in coding theory we do, so sometimes there is a little kind of little jump in the way we are moving now. So, we will look at like a generator matrix representation, because we want to systematically generate all the code words. So, linear code of now say dimension k. So, now obviously once you know that if you have information bit k, the number of, because it is because of the linearity, so the number of code words is always a power of q power k. Okay. So, linear code of dimension is actually power of k, and the length n over fq will have the following representation. What we do, always it takes say message symbols from m0 m1 up to mk minus 1. So, this accounts for k different elements from the finite field, and you have a generator matrix which is a k by n matrix consisting of k linearly independent code words. So, I can go to code word because I know the code word has a definition. Every code word linear sum is another code word. I will now pick k different independent code word, and that I will put that k by n, and if you look at this generation, that should generate all possible q power n elements. So, this straight away from the representation of a vector space, you get automatically the structure of a generator matrix of a code. So, in fact, when sometimes people studies vector space and all do not see, really what is really needed to you to see is basically the idea of this linearity and the finite field. So, the finite fields you understand very clearly, extend it to vectors, idea of linearity, you get a linear thing that becomes pretty clear. So, now one more idea of a concept called inner product. Sometimes it is used to help understand actually code. Now, we want to now understand a bit more about code, and so this is a new concept. So, one say inner product. Okay. So, inner product, let us take it as like a definition. So, we are allowed to make definitions, right, because we want, with using definition we can make new knowledge, right. So, definitions something like that. So, let u want so basically this should be u0 u1 up to un minus 1, sorry, yeah, this should be v0 vn up to un minus 1, both belong to fqn. So, you correct this one 0 to n minus 1, 0 to n minus 1 belong to fqn. Then we define inner product as simply you take pointwise multiplication of these two vectors and sum out all the results. So, it is basically ui times vi from I is equal to 0 to n minus 1 here, again as a mistake. So, if u times v is 0, then u and v are orthogonal. So, if this inner product is it turns out to be 0, then u and v are called orthogonal. So, this way you can have an orthogonal matrices. Idea of an orthogonality comes with inner product. Okay. Yeah. So, now let C and K a linear chord. Now, I define what is called a dual chord. So, for any linear chord now, because of this I have a dual chord that is also has a representation as C perp is the linear chord defined by you consider all those vectors of length n such that the A times C transpose, which is that is what we define as the inner product, is 0 for all vectors. Okay. So, take the code word and it take the other all the elements in this and the times. So, where the transpose represents the matrix transpose operator. So, let us take for example here take A belong to so A0 A1 up to A n minus 1 and C is a code word. So, C0 C1 up to Cn minus 1. So, this is 1 times n vector, this is n times 1 vector. So, what is the result? So, you basically you take A0 times C0, I times Ci from I is equal to 0 to n minus 1 and it just add up modulo q. Now, if this turns out to be 0, so I pick up all those vectors of length n minus 1 which are orthogonal to the code word. And so when I have a linear code words which are linear and everything, now I can I go to the space and look out all the code words come on in and I will look if they are all orthogonal, I will put them in a separate basket and that code is called the dual of a code. Okay, so see the definition. So, once we know the definition we will start making some inferences on the properties of this dual and that starts getting into. So, let H be the generator matrix for a C perp. So, now what we do, so obviously once it is that is also linear because if you have because we are only taking from a linear code words. So, you can easily show that is also will be linear. And so, then once you have a when it is a linear code, it will also have a generator matrix. Let us call that as a H, another H matrix. The concept of duality, whatever we talked about now, that leads to parity checks for the code. So, you have been sometimes know the parity check is something different. It actually comes from the duality, and so that is why I wrote some of these things specifically for this purpose. So, for any code word now C and let us take the C hat belongs to this, the duality implies that C hat times C transpose is 0. So, in particular this applies to the rows of the generator matrix that I called about for the real thing. When it is true for any two code word, this concept should also apply for the rows of the generator matrices. So, that is what we do. So, it then implies that you take H and C whatever the C transpose is 0. So, and that is what the parity check matrix of a code, nothing more than that. So, for all C we can see. So, result is that the generator matrix for a C perp is the parity matrix for C and vice versa. So, if you know the parity check for the things and you can do generator matrix. Okay. So, now once we have such a thing, so we would like to have a canonical representation for the code on G and H matrices. So, what is that canonical matrices? So, what is that? Any linear NK code has a generator matrix in the form of this canonical form. So any generator matrix we know it is always so any generator matrix of the form. So there are k rows, n columns. So k rows here, n columns here. And so obviously what it says is that you have a ik all generator matrix, you will have 1 1 here, rest are all 0, and there are some elements that tells you about the parity. So the structure is like this, where ik is identity is given here, and all other the matrix A is actually tells about the parities that present in in the code. For example, A11 and so forth. So generator matrix has this matrix. So it's let's call a companion matrix A, for example, in this case. But because any linear code now is a linear sum of these two these vectors. So you can say that here in this case binary case, for example, or it's actually this is true for G of Q. There is nothing like binary or anything in this case. It's any field is okay. So you can see that using one vector here, that's let us say a basis. How many different code words you can form over G of Q? Pardon? Q? No, that's for the whole code. I now ask you actually, I consider this particular one row, given this particular code word with the linearity assumption, how many other code words you can think? No, okay, let me make that clear. So of course any code word is a linear sum of these ones. So obviously there are q. So what I was coming through is that if this is a code word, so by rows of a code word is a code word, right? This is a code word. Now another any any scalar times this is also a code word, correct? So you got now let us say for example A times this is also a code word, B times this is also code. So totally how many elements are there in G of Q? 0 1 up to Q minus 1. So Q times that, and in particular 0 times this is also in the code word. So there are this particular row accounts for Q different code words, correct? So now you take Q different here, Q different here. So each column, each row gives you each of them is Q different code words, and when I now take a linear sum of all of them, I get totally Q to the power of K. So the size of the code comes automatically, and this is pretty obvious here in this case, because as you can see that whatever that is added here, this is an identity matrix. Yeah, this is a complete space of Q power K. So in the previous one when I mentioned the all elements in that G of 2 power 3 G of 2 3 which is can be obtained by so you can see that it's actually a linear sum of all of these. So this take 2 positions, totally get 8. The same way that's kind of thing. This is a canonical representation. Clear? So now let's take an exercise here. Convert the following. So what you do is that you have a generator matrix, which is a binary, and you want to you can actually divide into make it into a canonical form where the first k's are identity, first columns are identity, rest are all things. So and it's actually, do you know which code is that? 7/4 Hamming code. So but how do you now convert this into that? So let's try to do that quickly. So this idea this is being given, so obviously all possible 16 code words can be expressed as a linear sum of these ones. That's clear now. And so one of these two operations, what you do, this does not change the properties of the code. What happens is, first of all, you can rearrange the column, because for example if this is a column, this column, and if this column changes, really it gives a same code, but except that the bits in that position will be interchanged, and so it will never affect any properties of the code. So no problem with that. And second, since anyway code is linear, I can take any linear combination of that, that is still a code word. So, that is also not a problem. So, using these two properties, you can actually convert into this. So, first of all, because that I want 1 here, so which one I should move there? So, for example, I will try to make the first 2 bits, let us say my goal is to make 1 1 1 1 and rest I do not care, it will be something, but it should be a linear code, depends on that. So, I mean if I had a column like 1 0 0 0, I would have directly moved it, right, but there is none there, and so the next possibility is we will do the XOR of the first 2 rows and make it as a first row, right. So, first one is 1 plus, so you do like this, 0 plus 1 1, 1 plus 1 0, 1 plus 1 0, 0 plus 1 1, 0 0 1, right, then 1 0 0, 1 0 0, correct, that is the first one. Then for the second one, what will I do? Second and third we will do 0 1 0 1 0 1 0, clear. So, this is actually let us assume that 1 2 3 4 as a row, this is 1 exclusive or 2, this is 2 exclusive or 3, I can do that, yeah. So, for the third one, what would you do? So, now I can write down in the first step as it is itself. So, let us not complicate it. So, 0 1 0 1 and the last one is 0 0 1 0 1 1 0, right, okay. So, now we are what can I do now? So, I have to take the help of the first vector, right. So, now what I need to do, this the third one, this one and this one I can do in the next step, okay. So, I will put same thing here 1 0 0 1 1 0 0 0 1 0 1 0 1 0. Now, if I do this 1 plus 0 0 1 1 1 no 0 0 1, correct. And the last one I want, so what can I do? So, this one, the last one here, if I add with this, what will I get? 0 0, 1 plus 1 is 0, 1 plus 1 1 and 0 1 1. So, now it is almost like there in the final things. One more step, how do you do? So, now you can add this one to all of these, okay. Do you see that? You can 0 0 1 0 1 1, you can add to all of these ones, that will not affect the first 3 bits, it will only affect these bits and it will affect the last 2 bits. So, what I will do, this one because of this becomes 0 0 0, because 0 this will not change, because of these 2 all will change. So, 0 0 will become 1 1, this will become 0 1, this will become 1 0. And now we are. So, in fact, this time I did not have to even use the column swaps, okay, but you get this one. So, really you can see that there will be 1 1 1 0 1 0 0 1 0 1 1 0 1 0. So, this should be 1, sorry, this is 1 already. So, I can't change that one, it was there. So, 1 1 1 0 and 0 1 1. So, you can actually try this on Magma. So, for example, here I can, I use this things and go back here. So Magma is, as I told you, is a software developed in University of New South Wales, as a University of Sydney in Australia. So for example, here I can, so F2 is a finite field, and then I gave all the vectors that I chose, in the forms that were given there, and I run linear code over a finite field of length L and give all the basis vectors, and the Magma will give you the generator matrix in this form already. So you can start asking questions like what is the parity. So let's say I can make this one as a code 1 is this. So then say you can check C1 is this. Then you can say the parity check matrix of C1. I can ask, so it will give you the parity check matrix of C1. So if generator matrix is k by n, parity check matrix is n minus k by n. Okay, so automatically you see. So do you see the structure of now parity check matrix? You can see that parity check matrix also has, in this case it directly gives the parity checks there. It does it in that form, but the code it gives is in the canonical form. Okay, you can do like this, C1. And some properties of this code can be listed, and you can do a lot more things, study about the linear algebra through this software, because sometimes it's it's easier to learn through this. And okay, so let's come back here. So parity check matrix now you can also give it in canonical form, because now I can now represent G as Ik and all the matrices that I have here. You can take it as A. Now A is, what is A now? Let's say I will now write here. So G is Ik, this is the identity matrix of Ik, and you can represent it as A. So all this A is A11 up to A12 up to A n minus k and so far up to a k1. So it's a matrices, whatever that we don't care, and if that is there, then the parity check matrix so if that is there, then the parity check matrix from matrix theory, you can convince yourself that that can be easily written as H as minus A transpose, whatever that, and the negative of that, times I n minus k, where T is a transpose operation. So can we verify this? So what is the what is the relation, this relation that we should use to check this equation? So we need to look at the orthogonality, right? So we need to look at that. Say what we need to verify is we need to verify G times H transpose, because G is k times n, H is n minus k times n, but when we are trying to do the orthogonality, you have to take the transpose of that. So this is n times what will be n times n minus k. So then it will be this, this will give you k times a matrix which is k times n minus k, and I should get complete 0 for this one, correct? So how do I verify this? So you first take, now what is G? So what I need to verify is G times H transpose should be equal to 0, right? So now what is G? G is I k and then A. Now I need to take H transpose. So when you take a transpose, this will be n times n minus k, this will be k times n, this will be n times n minus a. So, this is that will be, this will be minus a, you agree with me, because you take over, and this will be I. So, this, remember this I has 1 0 0 0 0 1 0 0 up to k things, and then this will give you the elements of A, but when you run over as a matrix multiplication, you basically pick up the elements of A from this, and from this you pick minus A from this, A from here, this will actually is equal to A minus A. In fact, sorry, it is actually minus A plus A, and that becomes 0. So, once we have a generator matrix in canonical form, the getting a parity check matrix is quite straightforward. And you know, to get this idea, what we have done is we just use the idea of a linearity and a condition that of our duality, the duality condition. Okay. So, instead of actually getting a parity check matrix and looking at some equations, so just the linearity itself will tell us how this will perform. So, I cut short the usual discussion that takes place in the coding theory things, just to highlight the important facts. Clear? If you have any questions? So, you can take an exercise this and use this binary code and ternary code and write down the corresponding parity check matrix, convince yourself that is true. So, for example, in this case the ternary code, the equations is 0 1 2 and its everything is modulo 3. Okay. So, maybe can you help doing this? For example, G is this, what should be the H? The definition of H should be how much? It is a minus A transpose and I, that is the H, right. So, A is given as 1 0 1 0 1 1 1, and in binary case minus and plus are same. So, you can write now 1 1 0 1 1 1 and you put 1 here, yeah. So, this is a parity check matrix. So, you can take this one now, take this as a G times H, for example, take that code word. So, this actually is a generator matrix of the dual. So, take 1 0 0 1 1 1 0 0 1 1. So, it picks the 1 1 and you get a 0. So, you can verify that for each code word in G, you multiplied with the code words, there are 4 code words of them here, or let us take these 2 1 and multiply, you get 0. So, what because this fact will be used for decoding, because if there is no errors actually when you multiplied with a parity check equation you get 0. Now, whatever errors are there, errors actually pick up from that one, and that will actually leads you to the decoding. So, the concept is very important, but these two equations you can, this is the H for the first code, and what is the H for the second code, can you tell me? 2 1 1 0, next one 2 0, start with here, sorry, 0 1, okay. Why is correct? You can see that 1 1 2 0 is and it's, you have to take the negative and its transpose. So, this will be 2 2 and 2 0 1 0, that is fine, and this one. So, you can say 2 1 1 1 0. So, we will take the inner product of 1 0 1 1 and 2 0 0 1. Inner product means you multiply 2 times 2 0 1 1, 1 plus 1 is 2 plus 2 plus 1. So, then you have to subtract, right, inner product means you have to subtract. So, this becomes 1, this becomes 2. So, 2 plus 1 is 3 0, which is modulo 3 0. So, you see, try checking the inner duality for the ternary. You will, if you do not take the negative one in the for the thing, you will be in the things, right? You can try that one. So you will see that, you know, all these equations again. That's an exercise we do, and that's so. So this also tells us another relationship between the generator matrices and H because of this one. If C is a k-dimensional subspace, its dual has to be n minus k-dimensional because of the same property. And see also the generator matrix for C perp, which is basically dual, is parity check matrix for the C and vice versa. So if you know one of them, you can do other. So when you are analyzing sometime codes in any applications, if the code becomes very complicated, sometimes you can go to the dual and start seeing the solution, and it's pretty interesting. It comes you know, when you are handling with communication systems and other, depending on the case. So sometimes the core properties of the code can be better explained using dual, sometimes using the code, depending on the context. So that's what you will see. So because it's a huge difference. So you have let us say you take up a Hamming code which has a dimension of 7,4. Its dual is actually 7,3. Okay. Now 7,3 is basically you know, it's like called a simplex code, and simple, you know, so for all a Hamming code which is basically, let's look at the Hamming code's dimension. Tell me, what's the dimension of a Hamming code? Yeah, tell me. 2 to the power of m minus 1. What is k? 2 power m minus 1. Okay, and it has dimension 3. Its dual is it is 2 power m minus 1. Now it is n minus k, 2 power m minus 1 minus of this, which is m. And in general, this has a dimension minimum distance of 2 to the power of m minus 1, very high minimum distance. The dual, I mean, you can check that, and you know, checking that this is there all very some of the popular codes that is used always. In fact, that one is called m sequence. That means there are exactly m sequences, 2 power m minus 1 sequences, and all of them are actually cyclic shift of each other. So and that also has an optimum property in terms of correlation. So some of them are used for in your CDMA application. So one is this and that. So you can have got a, yeah. So I think the point to note from this talk is to actually consider a k-dimensional subspace, code as a k-dimensional subspace. Then its dual is n minus k dimensional subspace of, in the same vector space. So that's what yeah. Okay, so we'll keep it here, and so as I told you, we'll give something on the extended Euclidean algorithm that you can study and come back for that.